And in fact, while this topic is very much part of space situational awareness, it's actually an aspect of SSA that I don't think is even covered here in any of the talks, at least that I've seen so far. And that is the issue of how do you deal with active satellites, or in other words, satellites that can carry out maneuvers that you may not know about. And what we also point out is that that's also can be misinterpreted as erroneous models in the that you have for that space vehicle or that satellite as well. And this is work largely drawn from two of my PhD students, Dan Luby and Dard Ko. Both of them are PhD candidates at this point. So as we all know, the reason why we're here, in fact, is that one of the reasons is that the Earth orbital sphere is crowded with many different types of vehicles and objects. There's the orbit debris, nanosatellites, which are relatively a new, or CubeSats, a new entry into this population, commercial satellites, and military satellites. And there are a variety of definitions of space situational awareness, but one that's used a fair amount in the US is that SSA means discriminating, identifying, and characterizing all of the objects in orbit about the Earth. And one way of realizing this is by monitoring the entire population of Earth orbiting objects. Whether that's realistic or not is a different question, and not that one that we're worried about today. So within SSA, there are some topics of special interest. Some of these are special interest to us, some of them to other people as well. And that is identifying and tracking new objects or new orbit debris as it appears in orbit. Estimating non-gravitational models for satellites, because this turns out to be a limiting error source in how well you can predict where a particular satellite or debris will be in the future. Predicting future orbit uncertainty based on incomplete and noisy data, which is the orbit determination problem. And what I'm really sort of addressing here, not in its entirely, but the operations and capabilities of active satellites. And in fact, when you talk about active satellites and space situational awareness, there are some fundamental challenges. And the fundamental difficulty occurs when you have a non-cooperative satellite. This would be a satellite that you don't know what commands they're sending to do maneuvers or not. Most commercial satellites fall into this realm because they have their own operations. They do maneuvers whenever they want to do maneuvers. You don't know, but you may see after the fact that they've done a maneuver. And you may want to update the space catalog, say, in order to account for that. Another issue with these are poorly understood non-gravitational models, and then also propulsive models for these craft. And if you think about it, it's really necessary to distinguish and estimate both non-gravitational models for these bodies and at some level their propulsive model. Do they do a low thrust burn, or do they do an impulsive burn? Is it a very small thrust over a long time, large thrust over a short time? And with this information, if you can estimate both, at some level you can make strategic decisions based on the action or inaction of satellites. And you have to answer difficult questions such as how can a low thrust maneuver be discriminated against an inaccurate satellite non-gravitational model? So at some point they look sort of the same. They're both making the satellite drift, but one is completely natural, the other one is actually, they're heading somewhere. So one of the questions that we're dealing with as well is how can a maneuver or a mismodeling event be uniformly characterized in an unambiguous way. So what I'm going to talk about today, and really talk about it at a relatively high level, although it is a bit mathematical, so I will be flying through some equations. But are three different concepts that we've been working on over the last few years in this area of space situational awareness. The first is a concept called the control distance that we've developed in order to measure whether or not an object is potentially maneuvering or if it has some systematic model error associated with it. Another one is a method that we've developed using the control distance to discriminate between modeling errors and maneuvers. And then finally, a few slides about rigorous representation of non-modeled events. So the control distance idea that I want to talk briefly about first can sort of be summarized as follows. And these are slides taken from Marcus Holzinger. Let's say we have a satellite that's being tracked at some point. It has a state and it has a covariance, some uncertainty. And the way things work, we usually then propagate the satellite into the future. Its covariance grows a little bit. And we have a predicted place where we believe it will be. However, when you actually take measurements, you find that there's potentially the same satellite, but it's in a different orbit, slightly displaced from it, and has its own, once you take a measurement of it with radar, you can get a full orbit determination. It will have its own covariance as well. But ballistically, these two guys don't necessarily match up with each other within the noise of the covariance. And so it appears here that either you have a bad model for this satellite and it's actually being pushed at a slightly different rate with different accelerations because you don't know its solar radiation pressure coefficient or its drag coefficient very well. Or this object actually did a maneuver somewhere in this time span and is now actually in a different orbit. And the control distance idea is a way to take what could be quantified as deviations in state distance, which are very hard to interpret in terms of what an object has or has not done, and reinterpret them in terms of optimal control theory. And every time we have a state distance in orbit, we can actually correlate it with a connecting optimal control policy that would take this trajectory with this uncertainty to this later trajectory. And the value of this optimal control cost function indeed is that connects non-ballistic states is potentially a distance metric that we can use to measure the distance between satellites in orbit around the Earth. So that's sort of a graphical illustration of the idea. And what we're really interested in doing is measuring the distance between two orbit states and quantified by the control effort. This is an interesting problem because it brings together another aspect that theoretical aspect that I'm very interested in, which is optimal control theory. And in fact, optimal control theory plays a fundamental role and actually can identify, if you will, the minimum level of control effort needed to connect two orbit states. And what we've defined as the control distance provides this measure with some additional benefits. It is, in fact, a metric that you can use to rigorously measure distances between states in terms of control effort. It can be generalized to stochastic values, so you can have uncertainty distributions in the control metric, if you will. It can be defined not just for complete states, but for partial state measurements. And some of our research is actually focused on using this property to actually automatically detect maneuvers using a filter-like formulation. And you can also evaluate it for a range of possible cost metrics, although we have our own favorite one that we use. So the definition of the control distance, it's, and sorry it gets a little mathy, but it's really the value function of the optimal control law connecting two states. So here we have the optimal control cost. X is the state, U is the control. And the control distance is just the infim of overall admissible control policies of this particular cost function under the constraints that it follows the dynamics and under the constraints that it matches some terminal constraints. And this one you could think at time t0, the state should be equal to x0, the initial state, and at time tf, it should be equal to xf, the final state. And we actually have, from the Pointryagin minimum principle, we actually have a control policy that we can state for this particular problem. And if we solve a two-point boundary value problem, which is challenging in its own right, but can be done, then we can actually compute the control distance between two arbitrary states. So this is a metric because it satisfies all the principles of a metric. Positivity, and that's guaranteed by choosing our control cost function to be greater than or equal to 0. Strictly positive because the control distance is only 0 if you, in fact, are only connected by a ballistic trajectory. Symmetry, and this is just due to the reversible nature of our orbit dynamics. And it also satisfies a triangle inequality, and that's satisfied by the principle of optimality. We also have some choice as to what control cost function we use. There's actually two very popular ones. For spacecraft mission design, we often use the minimum fuel metric, which is a simplified version of it is just the norm of the control acceleration, the magnitude of the control acceleration. The other one that's often used is the minimum energy or the quadratic cost function. This one in some ways is more realistic, but it gives us a discontinuous control structure in time and gives us impulsive maneuvers if we allow it to. And it's computationally very challenging to solve. Even linear systems present some real barriers. So what we prefer for the control distance is actually this minimum energy because it requires no upper bound, has a smooth control structure in time, and computationally it's much simpler to solve. And in fact, for a linear system, there's a simple closed form solution for this. You can also generalize it to stochastic values as well. I'm not going to go through this, but just this sort of walks you through what the mean and what the sigma is of the control distance in terms of Gaussian distributions. So that's the control distance, and we found a variety of different ways of using it to correlate to satellites that may or may not be the same just by looking at the fuel cost associated with going from one state to the other. But another problem that we're solving with it is sort of this discrimination problem. Because if you think about it, the control distance by itself doesn't tell you, or it can't distinguish between whether you have maneuvers or modeling errors in your system. All it does is it measures this distance between the states relative to the model that you have. So a good question is it possible to uniquely ascribe a force model error to a non-zero control distance or a maneuver? Now what we find in SSA is that the systematic force modeling errors mostly arise from object-specific non-gravitational model deficiencies. If you think about it, we know the Earth's gravity field extremely well. We know where all the planets are, so we have all the third-body gravitational perturbations extremely well defined. What we don't know is, and even some aspects of the non-gravitational environment can be characterized, such as the upper atmospheric density fluctuations and the solar constant and the like. But each satellite has its own unique non-gravitational coefficients for drag interactions and for solar radiation pressure interactions. And these we don't know a priori, and these tend to be highly uncertain. Now, if we actually look at putting in modeling errors into that dynamics and computing control distances for those objects and looking at the control policies, this is some work Dan did a few years ago. What we actually find is that the control policies mimic in some way the natural dynamics that we were mismodeling in these particular examples of mismodeled drag, SRP, and combination of drag and SRP mismodeling. So this gives us an idea that we can, if we assume a basic control distance computation, and if we assume that the non-gravitational forces are modeled, in this case using cannonball models for solar radiation pressure and for drag, where these coefficients C, SRP, and CD are potentially uncertain, we can then use the control distance and the optimal control profile to actually do an estimation of what the corrections to these non-gravitational parameters should be. And if we can drive the control distance to 0 by estimating out these non-gravitational uncertainties, then we can say that there was no maneuver that occurred. But if we drive out those errors in the force models for the non-gravitational forces, and there still is some finite control distance, then we have better confidence that a maneuver may have occurred in that system. So we can go through a simple least squares derivation. And here's one example from Dan Luby's, where we estimate drag and SRP just using the control distance. And here we placed a 2.5 meter per second cross-track impulse into a sequence of many days of data where we have state estimates every 20 hours with a certain level of uncertainty ascribed to that. And the control distance metric over each one of these 20-hour gaps is computed here and shown, and we have this distribution. We have this one outlier, but these are all statistically significant. When we apply this algorithm, we can actually derive most of those control distances down to below level of statistical significance, but still identify one segment where there is indeed this control maneuver that occurred. And here we actually show the estimated value of the drag parameter, and it statistically is scattered about the true value, whereas initially we had this error model of zero drag for this particular example. So a second question that I'll just touch on in a few minutes is the representation of spacecraft events. And this is work being done by another PhD student, Dard Ko. So when we do have these maneuvers or gross modeling errors present in tracked objects, what they really represent are events that cause the state to deviate. And while we can, with the previous work, characterize these using optimal control policies, what we're searching for here is a more fundamental basis with which to represent such events. And here we leverage some work from a previous PhD student, Jen Hudson, which essentially says that any infinite dimensional control policy applied to an orbit over some finite time period is equivalent to an average control policy that only consists of the 0th, 1st, and 2nd Fourier series coefficients in terms of eccentric anomaly. And this is an interesting result. What we have here are the Gauss equations with control forces represented here, and we could express these as arbitrary functions in terms of a Fourier series in terms of eccentric anomaly. So any viable control can be represented with these Fourier coefficients. If we take these and if we average them, we have the remarkable result that there's only 14 of these coefficients remain, and they're just of order 0, 1, and 2, even if that original series had an infinite number of terms. So what we're doing here is we actually use the fact that there's a finite basis of control coefficients that actually represent all secular changes in an orbit. And we can utilize that fact. In fact, we can reduce it down to just 6 coefficients, which are outlined here. And it turns out that any change in state can actually just be represented by unique values of these 6 coefficients. And here we see an example that we have a change in orbit elements from here to here. And the secular solution, just using these 6 constants, brings us from the one point to the second point. And then the actual Newtonian numerical integration follows this along quite closely. And essentially, what these form are an essential set for thrust coefficients, and it provides a unique representation of any unmodeled force or thrusting event for a satellite. This can be used for an estimation scheme to fit data across events, and it can also be used as a direct representation of the optimal control policy I talked about before, to speed up computation of control distance. And here's an example of one delta V over a several-hour time period and what it looks like in terms of these Fourier coefficients. So just to end up, a very brief overview of what we've been doing. Optimal control theory can be used as a strategic tool in SSA applications. We can apply it in a rigorous manner and use it to apply constraints in characterizing satellites, can form the basis of strategic decision making, And then averaging theory can be used to derive fundamental representations of unmodeled events. It can be used to represent arbitrary model errors or maneuver events, and provides a unique basis into which any unmodeled events can actually be represented. So, thanks.